Hello, welcome to this tutorial section. My name is Godwin, and today we'll be designing a microstrip patch antenna at a resonating frequency of 2.5 GHz. As you can see from the diagram, there is a microstrip patch antenna, and it has a patch and a feed line. And the parameters which are key over here are the width and length of both the patch and the feed line. If you're able to get the width and length of these two parameters, then every other parameter won't be that big to deal with. And before you can get these values, it is dependent on the dielectric substrate and the resonating frequency. From antenna class, we studied that the width or the length of a microstrip patch antenna can be calculated using this formula, that is C divided by twice of the resonating frequency times root of the expression dielectric constant plus 1, all divided by 2. The calculations are quite intensive for microstrip patch antenna, so emtalk.com grants us with a calculator which we can use to compute the width and length of both the patch and the feed line. So we go to emtalk. This is how it looks like for the microstrip patch antenna. So we feed it with the dielectric constant. In my case, I'll be using FR4 with a dielectric height of 2, resonating frequency of 2.5. After that, you input the impedance, that is the edge, and that you simulate, and you have these values. After that, we can go to tools and tutorials. We can go to calculation, microstrip line calculator, and same over here, we input our constants. I have 2.5, 50, 90, and our synthesize. These are the values of the line, the feed line that we're using. So we move back to HFSS and start our design. Go to new project. Alright, so I will insert HFSS. In my new project, I will insert HFSS. As we saw over there, we have a patch which has dimensions. So we can name it patch over here. And dimensions of the patch were, the length was 28.085, and the width was 36.514. So we want to divide that directly at the origin, so we do minus 36.514 divided by 2 of minus 28.085 divided by 2, and our height of substrate is 2, but we are dealing with the patch right now, so we have to elevate it from the origin. So this is all we have in, so we can do fit to all so that we can manage and do our design with. Alright, so this is what we are having. Good. So we can now introduce our feed. Our feed is 3.8 by 16.4, and it should touch the edge of the patch that we are having. We can rename it feed line. So it is 3.8 by 16.4, but what we should note that in the x direction, so you will be having minus 3.8 divided by 4 divided by 2 rather. But what we should know that in the y direction, it will be the width of the patch, half of the width of the patch. That is where our feed line will start from. So we have 28.085 divided by 2. It will touch just the edge, and this is what we are looking for. We forgot to elevate it, so I'll do it again. Alright, so we can now match them. Unite. I don't want to forget about assigning material, so I will assign it before I move on. PEC, perfect electric, sorry, that is for the patch. I'm done. You can view it over here. Good. Okay, so now I want to introduce my substrate. I want it to begin just at the edge of the feed line. So I'll zoom in, try my possible best to do it. I have to go for this, put it on the edge. Also, I will name it substrate. And assign its material to it, FR for epoxy. For epoxy. We can't have 76, it's too much. The height is 2 and it will begin from the origin. Good. So we will let S move further because it doesn't cover the whole patch. So we will have twice of 23.9 by 2. We have 47.8. 47.8 in the S direction. We do 47.8 divided by 2. Good, everything is on point now. After here, we can introduce our ground. Of course, we can't forget about it. Good. I want to assign the material so that I don't forget about it. So perfect E for ground. So we've assigned FR4 perfect E to ground and patch. Okay, so I can change the color so that it becomes easy. Okay, I think the ground is still on the top. Let me check. Oh, the ground shouldn't be elevated to 2, it should be at 0. Great. So now we are left with the pot. So I'll change the plane that I'm working in to Z. That is where I can assign my pot. We'll zoom in. I'll have to zoom in again. To zoom out now. Alright, let me escape and align my 10 wall. Let me plan it. It's okay now, so can rename it pot. Assign the excitation. Excitation simply means we are assigning the signal at that point to the antenna. Define my line when it changes to triangle. Yes, triangle to the top. I will expect the triangle to, and I'm done. Define with no error. I'll change the color. Change the color. This will be fine. I'm left with a radiation box. I'll change the plane to SZ so that I can work in perfectly. To radiation box. Usually it is assigned that the distance from the antenna to the box on each side will be lambda by 2, but maybe how it is assigned will be okay. So now I'm having a box. I'll call it radiation box, rad box. I have to change them. 0, 40 will be fine. I'll divide it just at the middle. Alright, so I'll make it transparent so that I can see my antenna within. Alright, everything fits well. It looks like I should along Y, I should expand along Y. So along Y, let me do 100. Okay, it's fine now. Everything is aligned perfectly. I can now introduce excitation or boundaries to my radiation box. Boundary, go to radiation. Okay, so I can now check my ground is given a boundary, patch, radiation a boundary, excitation also available. So you have to introduce a partial setup. So now I will introduce my analysis setup. I'll do 25 passes with meeting frequency of 2.5 and proceed. I'll start from 2 and that's 4. I'll use linear step 0.001 is okay. I'll change interpolating to fast. Can preview. This is my band. Can close it. Do okay. Everything is fine, so we can start our simulation. Have to rename the project patch for telecom for telecom 3. Alright, so you have to wait for the simulation to be done. Alright, simulation is done. I believe we have no error. Simulation is done with no error. So we can go ahead and analyze how our antenna performs. So we will look at the reflection loss. Check that it is in dB. Plot. Alright, cool. So usually we have a standard that we check, that is -10, and it simply means that when the antenna, when the reflection loss crosses the -10, it means that we have most of the voltage or the current that we fed with the antenna being transmitted with least error. And in actual sense, the reflection coefficient that corresponds with the -10 is 0.333. And when you compute the loss, you have the loss to be around -10 dB, which is fine according to theory. And we can see where our dip has shifted to. For patch, it has a lot of issues, and you can shift this dip back to 2.5 by using optimization. So we go ahead and look at the voltage standing wave ratio. So we select VSWR. We don't plot VSWR with any unit, we plot it in normal scale. And with the VSWR, we look at 2. So I can change this scale. Can start from 0 to 8 with a step of 1, so that we can see how this thing performs. So we can trace the 2 and check the bandwidth of the device. It will be around this side. the difference between where the two crosses, that is this point, then that point. So we can go ahead and look at our radiation pattern. So go to far field, radiation pattern. We'll change it to sweep. Gain total, dB. Theta will be the principal sweep or the family, the principal sweep over here. And go to families. We don't want to plot all of phi. We just plot 0 degrees and 90 degrees. We can generate a new report. Alright, sure. So this is actually the H-plane of the radiation pattern. We will understand it better when we plot the 3D polar plot. So we will go ahead and plot for the E-plane 2 far field radiation pattern. Gain dB. Now we change our primary sweep to phi, and we plot all of phi. Go to the families and plot just 0 degrees for theta, as I said. So it is a directional antenna, but the gain is very low. You can consider it to be so there. At this point, we have most of the energy radiation in this direction as compared to this. So it starts from somewhere -10 and propagates the signals in this direction with a maximum gain of 2.8, which is okay, but usually for patch it should be more than 2.8. So I will end the video here. Thank you.